Let's now talk about those curved mirrors. The first kind is concave mirrors, as you can see in this solar cooker, which uses the sun's energy to focus in on this sort of sheen surface to cook the thing that's in the pot. So concave mirrors are mirrors which cave inwards. So you think cave, it sort of like bends inwards. Um, Now this statement here, reflective side along the inward curve. When we're talking about a mirror, there are two parts of a mirror. If I just draw it up here, you have the inward curve, which is where it curves inwards, and the outward curve is this back bit here. Now, to differentiate between a convex and a concave mirror, we use these dashed lines to indicate the back side of the mirror. So this front bit here, where the light rays are actually coming in and out, this is the sort of silver part of the mirror, like the polished side of it. And these lines indicate back side of the mirror that the light rays don't actually hit. And I can't believe there's still birds outside. So concave mirrors produce both real and virtual images depending on where the object is placed. The axis running through the extrema of the mirror, so the extrema of the mirror is the center bit, so the bit that sort of either, if you're talking about the polished side, it's the one that bulges most inwards, but the non-polished side is the one that bulges most outwards. That's known as, oops, it's not there. That's known as your extrema. And the line that runs through the center of the extrema is known as, well, part of it is known as the focal length. So the focal length is actually the length required so that you could actually trace out a circle. So think of it similar enough to a radius. If the object is outside of this focal length distance, so between the focal length and the extrema, also known as the pole, if the distance between the object and the extrema is greater than f, then the image will have three different properties. It will be real because the rays will intersect. It'll be inverted, which means just upside down, and magnified, so it will actually appear bigger than it actually is. However, if it's inside the focal length, it'll be virtual because the light rays don't intersect, upright, and diminished, which just means shrunk. Yeah, and as I said, solar cookers, which is this thing here, is an example of using a practical application for a concave mirror, but also dentist mirrors can also be used just to create that extra zoom when they're looking at your teeth. The second kind of mirror is a convex mirror, which is one that bulges outwards. So it's on the outward curve and it looks a bit like this. So we have the shading bit here, light ray coming in, light ray coming out. So it's on the outward curve and the extrema is again in just the same point where it bulges the most outwards. So no matter where the object it will be placed, it is always virtual, upright, and diminished. And applications of these include driver's mirrors and anti-theft measures. So it essentially, that's where you see all of the notices saying that objects may appear closer than they actually are on some driver mirrors, which is something that you are taught as when going through your driver's license. So we're now going to look at ray diagrams of these mirrors. So if I just draw the concave mirror and the lines for it, this right here is the extrema, then we have the focal length, and then the center of curvature. So the focal length is like halfway between the extreme and the center of curvature. So I do apologize for that. Um, Now, there are a couple of light rays you need to know. If it goes into the extrema, it goes out of the extrema at the same angle it came in. So these two are the same. And the two are kind of, the next two are kind of opposites of each other. If it goes through the focal length, it comes out parallel. And if it goes in parallel, it goes right through the focal length. So those are handy ones if you want to draw ray diagrams. You can figure what happens if a light ray goes through the center of curvature. It is a bit of an interesting one. Now for a convex mirror, this is where things get a bit weird, and we have to draw some extra things. So we have, again, the focal length, the center of curvature, and you can also put a focal length and a center of curvature behind, mostly because again, same, if it goes into the extrema, it goes out of the extrema. If it goes in parallel, however, um, normally it would go through the center, or it would go through the focal length. However, the focal length is actually behind the mirror. So what we do is we pretend this ray goes to the focal length, but then out. So this is where our actual virtual image stuff comes in. So the light will head in both ways. It will hit the focal length and then go back out as if it's coming from behind the mirror, and vice versa. If it goes through the focal length, it will go out parallel. Again, you can figure out what happens if it goes through the center of curvature, but those would be the more popular ways to draw. So whether it's the focal length parallel or in or out of the extrema are the most popular ones asked, and will get you um, will get you enough places.